In this video, we're going to cover the solution to the polymer production regression problem. And if you come down here in the machine learning for engineers course, down to the polymer regression. And if you select this, you'll see the problem description. And I'll just start with, my experience is I've worked in industry for about 7 years on these types of reactors. The one that's shown right here, that's a unipole reactor, but I've worked on many others, including butyl, rubber, polypropylene, polyethylene, polystyrene, and others. And one of the important things in these reactors is to be able to produce the right product, such as density, melt index, or melt flow rate. Those are this density and the melt index, melt flow rate. Those are related to viscosity of the polymer and also some of the properties and how those change as they process it or make their different products, whether that be a car bumper or a washing machine drum or a bag. So those must be kept within tight specifications for each customer and each grade. So the different types of products need these different properties, and sometimes you transition between those in the reactor. So this case study is to analyze the polymer production data to predict a melt flow rate or measure of viscosity of the polymer. So here's a gas phase reactor. They're also slurry reactors, but this is a fluidized bed where this is the bed where you're producing the polymer, and then it increases here in the cross-sectional area of that reactor so that the velocity of the gas decreases and the bed stays here, and then it recirculates around. You have some heat exchangers to remove the heat, and then you re-inject here from the bottom and fluidize the bed. So they have chemical building blocks like ethylene, propylene, you have butene, isobutene, and others. Catalyst is injected with the monomers under these carefully controlled temperature and pressure conditions cause this reaction to grow the polymer chains. So hydrogen is this thing called a chain transfer agent to stop the growth of the polymer chain. So the more hydrogen you add, the shorter the chains, and it makes it less viscous. And one of the measures of this is the melt flow rate, or the melt index, is commonly used in polyethylene applications. So we have different properties that we use to control the tight grade specifications, and we have some case study notebooks. But let's just cover the objective here first, is to develop a prediction of the reactor MFR from the polymer reactor data set. We're going to report an R-squared and for predicting the natural log of MFR in the test set. The randomly selected values that split the data into 80% for the training and 20% for the test set. And we'll use linear regression and neural network with multiple layers for deep learning, another regression method of your choice. And we'll discuss the performance of each, and then we'll submit the source code in a summary memo. And this just shows the coding part of it, and then you'll need to make sense of that, create your figures, and generate this summary report. So regression, we can use any of these regression methods. There are others that are listed here as well, such as the XGBoost regressor that you can use as well. Okay, and from the data set, I took this from Kaggle, a publicly available data set, and there were only these types of data tag names for the columns, and just experience in this area, and looking at the values and there are no units there, but you could see things like flow. That might be a hydrogen ratio of some sort. Maybe this is like a pressure in the reactor, a level. There's another flow. So this might be a comonomer. So propylene and ethylene, so some type of impact copolymer or some other type of, looked like a fluidized bed reactor. And then you also have maybe the catalyst feed rate, and then a temperature of the reactor, and we're going to use all of these conditions right here to try to predict the MFR. So the data set has missing data and outliers, so we'll need to do some exploration. And we can use these modules right here, the data science modules, to help us along the way. All right, and here's the original MFR data if you'd like to go onto Kaggle and see that. I've also made it available here, so it's easy to import it into the notebook. Okay, so let's get started with this notebook, and I'm going to just come back up here to grab the notebooks. Here they are in the GitHub archive. We'll just go ahead and download all of the code, and you can also just clone the repository or just download it and extract it. And the only one that we need here in this PDS main is this MFR regression. So I'm going to cut this one out right here and delete these other folders. Okay, so inside here are these notebooks, and we'll also have this additional fifth one, the Intro to TensorFlow and PyTorch. Okay, so let's go back to the web page here, and what we'll do is just open up these notebooks. All right, so here on the desktop I have this MFR regression. Okay, so MFR regression, and then I have this first notebook right here. So let's just jump in here, and as we go along, I'm also going to just share this map of where we're going with this, and this is a map that we use in the course. We're going to identify first of all the business objective. We want to try to predict MFR to have better property control. Right, and we don't necessarily need to go this way because we have data. But if we didn't have data, or we had a good simulator, we could supplement that with this physics-based digital twin. So we're going to go this route and do some of the data consolidation, look at some of the plots, be able to visualize our data, and then assess the data. All right, and sometimes we'll need to do feature engineering to add additional features. But in this case, we'll do this outlier detection and filters. We'll scale the data, and then we're going to split it and come up with our train and the test set or the validation set. And then we'll come over here. We'll say, does it have labels? Yes, it does have labels. We're able to see the MFR. So we're going to do some supervised learning in this case with regression, because they're continuous numbers, not discrete values. Okay, and then we'll look at the performance of this as well. So this is our overall roadmap right here. I'm going to just go ahead and erase this, and as we go through this, I'll just kind of mark on this what we're doing along with each step of the way. Okay, so let me make that just a bit smaller, just so we can mark here where we are as we go through this journey. Okay, and I'll bring this one back over, and make a little bit of room for this one. Okay, so here we have our URL for the data, and what we want to do is now just import this data. So I'll just import pandas, and this is a good way to just be able to work with data as you import it as PD. There's our URL, and one of the things we can do is just import it directly, call it data, and I'll have read underscore CSV, and this is going to be URL, and then I can put the data head. Okay, so there is all of our data. We're just going to rename some of the columns here. Now, based on what we saw there, I'm just going to copy these in, but you can use these as well. I'm going to rename these based on the table that we saw in the document. Okay, so I've just renamed those to get rid of some of those more confusing tag names, something that makes a little bit more sense. All right, and then the other thing that we want to do here is also add a new column. So this is the natural log of MFR. a lot of times this is a better way to express the data because we have such wide-ranging values that we're linearizing it in a way between the hydrogen value, the hydrogen ratio, and the MFR. So this helps with the correlations, especially for linear regression methods. If you take the natural log of the MFR versus the regular MFR. Okay, so I need to import NumPy here. And there are my data values. I can describe it as well. I don't need the 10 in there. Okay, and then it gives me some of the statistics about this. Okay, now let's go down to, okay, so I've renamed those. I created a column for the MFR. If I hit, I can just delete these. DD deletes it. Okay, so there I have the describe. I've imported it with these different column names. All right, let's use pandas profiling now. If you don't have it installed, you can run this command in one of your cells and it will install it. And then you may need to enable your widget extensions to be able to view this. All right, so here we go. I'm going to import it. If not, then it's going to run those commands. Okay, it looked like everything is okay here. And so what I want to do now is use this profile. So many of these you can just copy the code, go ahead and put it in, and then run it. There's my profile. And then I want to put it out to a widget. Okay, so profile to widgets. And open and close parentheses. All right, and this is going to generate a profile of my data, and this one's nice to be able to summarize a lot of the data, much more than this describe function right here that just gives a table. This other one is going to give us much more analysis. It's a little bit slow for large data sets, so sometimes you want to include the minimal equals true. In this case, the data set really isn't too big, so we're going to go ahead and use the full data for this and some of the correlation analyses. All right, it generates this widget right here where we have a number of observations. We just have 2,500 missing cells. It gives us a percentage there, gives us total memory. There's some warnings here as well. Okay, so we have high correlation with, and this makes sense, these are just functions of each other, so picked out that we have high correlation between those, so possibly duplicates there. All right, and here we have some of the variables. It profiles each one. You can see a distribution of each one. So pressure is tightly controlled, probably to 31 bar or so. Okay, level, this is the bed level. This might be in terms of tons in the bed. Here's C2, and you can see this is a flow rate, so pretty constant production rate. Sometimes you have a little bit lower, a little bit higher. Here's the catalyst flow rate as well, so you can see the catalyst productivity versus what you're injecting in terms of the monomers. Here's the temperature. This one's really critical. If you go too high, you can have reactor runaway. So this also greatly affects the properties in most polymer reactors. All right, and then we have the MFR. And this one's kind of interesting because we have, this one is a very high viscosity polymer right here, and this was a low viscosity. So what happens with this MFR is you heat this polymer sample and put a plunger on top, and this is the number of grams per minute that come out of that dye. So if very few grams per minute come out, it means it's a very high viscosity polymer. And you can see many of the data sets are this high viscosity polymer. There's also quite a distribution of other MFRs between 10 and 20. Okay, and here's our skilled for the natural log of MFR. Okay, so let's go on to the next one now. So this was a bit of our data exploration. We took a look at our data and we consolidate it. We have all the data together, and then we are going to go on now to visualize this and clean up the data a bit more. Alright, so let's go on here to the visualization, and there's just some packages that we're going to want to use here. Matplotlib. You don't necessarily have to have this in newer versions of Jupyter Notebook, the Matplotlib inline, but I'll just put that in there. It doesn't hurt to have it. And then we have Seaborn that we're going to import, and then also Plotly Express as well. Okay, so let's go ahead and just import the data, and this one we're going to first of all just copy this code here. So import this data, and then just like we did before in the prior one. Okay, just so we have that same data set that we're starting with. And then the other one that we're going to do here is just drop any rows with not a number. So that's one way to just clean it up, so any of those that are missing values, we'll just say, you know what, we've got enough of them now. And let's just look at the length of data. Okay, so we started out with maybe dropped about 100 or so of those data points. Okay, so there's our data with the ones that are dropped. All right, let's go down to a pair plot. So this is going to be the Seaborn package, and I'm just going to use this SNS pair plot of the data. Okay, and it's going to run. This one takes a little while, and let's see what it produces. Here's our pair plot. Now it's a little bit hard to see here. C3, H2R, pressure, and then you can see down on the bottom there's C3. So the ones at the diagonal, those are going to be your distributions. Like we saw before, it's the ln MFR versus ln MFR. So that one is, that one makes sense. It's just going to be the distribution of itself. And then these are the ones that are highly correlated. We just took the natural log of that. So you can see it's highly correlated between MFR and natural log of MFR. Okay, and then you can see the other ones as well. What we're looking for in particular, for example, is H2R. How does that affect the MFR? Okay, or the pressure, or the level C2, the catalyst, the temperature as well. So all of these are data points, and what we want to do is try to be able to discern, just look at this graphically and see if we see strong correlations, okay, for example, between the hydrogen ratio and this MFR. Okay, so as you increase the hydrogen, this MFR should go up. All right, that's our data from the pair plot. So we are now looking at visualizing the data. We're doing correlations, distributions, and pair plots. All right, let's go on to a joint plot now. Make this just a bit smaller so we can see everything on the screen. Okay, there's different types. There's the KDE, the hex, and REG. I think it might be regular. I'm not sure on that. Okay, so I'm just going to do a joint plot now. And here you can see KDE, but if you change this one to REG, okay, there it shows you this H2R versus ln MFR. And this one's a little bit interesting because it shows this distribution of that variable here, but then this pair plot and this relationship between them. Okay, and let's go to hex as well. This one's makes good wall art here. Okay, and then just Control Enter to run it. Okay, and you can see just kind of this cluster, almost like a population density map or something of where the data is. All right, and then let's go on to try count plot to show the number of bin samples of natural log of MFR. Okay, so it bins them together. You can see the different distributions of these and the counts of each one and how frequently they occur. Okay, so that's nice as like a histogram. The axis didn't turn out very well. There's a lot of values there. So there's probably some ways that you can bin those differently, create fewer bins to be able to see the numbers and the values. But it's almost like a continuous distribution here, and it's trying to bin them into different values. Okay, let's create a correlation heat map now. Okay, this one is interesting because anything that is a darker color, okay, in the positive one, or if you go negative as well, it has a negative correlation. You can see a very strong correlation between these two, and that's why it gave us the warning. Is these off diagonals are nearly 1 because it's just the natural log of itself. The other ones along the diagonal, those are going to be 1 because they're obviously correlated to themselves. And then the off diagonals, we're going to be looking for these. So for example, the hydrogen ratio, that one is going to have a strong correlation to some of these other values here. And you can see it's symmetric. So as it comes, let's see, right here. Here's the symmetric value. So really you only need the bottom half of this, but they just put it into this mode. So you can look at it by C3, for example, how that affects all of these, or C3 on this side. Okay, so you could see any of the dark ones. Those are going to be the ones that we want to pay attention to. You have some of these like C2 flow and some others. Now, one of the things that if you know about polymer reactors, it really isn't the flow coming in. It's more about the concentration inside the reactor. So some of this we may need to modify it so that we get hydrogen to hydrogen ratio. That might be hydrogen to C2 or hydrogen to C3 ratio. I didn't really have, I just had the tag name, so I'm just kind of guessing here on what these are. Okay, the temperature, that also might have a very strong correlation, but there may not be a lot of data diversity there. You notice that the temperature was always at mostly a single value, and they don't typically change temperature in the reactor. So even though it may have a strong correlation to the properties, it may not show up here in the correlation matrix because there just isn't enough data to show that. Okay, let's go on to the next one now. This is going to be preparing for the data for regression. All right, and I'm just going to copy this code in again. All right, and it's going to import it as a data frame just like we've done before. Okay, now there's several different types of graphical techniques to help detect outliers. So a box or histogram plot shows outline points. There's also various statistical methods. So if you don't want to do it graphically, you can also create conditions or other things to be able to eliminate some of these outliers. Now what I'm going to do here is, I don't like some of these. The temperature had a big excursion here. They likely had a reactor runaway. I only have a few points up here for the MFR. That might have been a big transient, maybe some bad samples there. They don't maybe regularly make that. So you also have the bed level and the hydrogen ratio. Maybe it went really high on just one occasion. So these are areas where we may consider filtering out some of the data. And there are statistical methods to do that, but let's say you know something about the process and you say, yeah, if my reactor temperature is ever above 85, it goes into a quench sequence. And so this is really not good data because I'm just trying to save the reactor and prevent it from removing the fluidized bed and agglomerating the polymers. It has a temperature runaway. So maybe you eliminate some of that because you just don't maybe make these grades or something else. So the box plot is nice because it shows you the different quartiles of the data, and then it shows you potential outliers here as well. So let's go ahead and just remove some of these. I'm just going to start with this, where if you run it, then it's just going to remove those values. So for example, on the hydrogen ratio, if I'm going to keep anything that's below 0.7. So I'm going to cut it off right here. I'm going to cut off that point. And then also I'm going to say it has to be greater than 0.01. Hydrogen ratio of 0 really doesn't make much sense. I want to cut out these values as well. So if I cut those out, then I have, I can do that with pandas very easily. I can just say my data for the hydrogen ratio has to be less than 0.7 or greater than 0.1. Okay, but let me add a few others here as well. I'm just going to add, let's see, a couple others like the C3. I want that to be less than 100,000. Okay, so let's see, this one already is less than 100,000. Maybe it's a C2. I need less than 100,000. Let's do that one instead. So I'm going to filter out that point. Maybe the MFR has to be less than 30, so I want to cut out these points right here. And the temperature has to be also less than 86. So I'm going to cut out those two right here. Okay, so here it is, and then let's just do this box plot again just to verify that the set does not have outliers. Or has fewer outliers, I guess. Okay, so here we have it. There's probably, again, based on specific information about the data, you might be able to construct better ways of doing this. You can also do some ands in here, so if multiple conditions are met, then you'd keep that data. Okay, so let's do remove MFR and only keep the natural log of the MFR as ln MFR. We can delete that with this command, del, and then the data, and then put our name in there. All right, so let's go ahead and do that, just deleting this out of the data set, and we'll do data.head. Okay, so you can see that I've removed MFR there. So I removed one of my columns, and this is also part of the cleanup because I took the natural log of this, and now I don't want the MFR, the original one, so you can remove features or labels. Okay, so now we've assessed the data, we've cleansed it. So here we are on the flow. We have clean data. Now we're going to be moving over here to the scaled data. Okay, so we're going to scale it either with a min-max or a standard scaler. And min-max scales it between maybe like 0 to 1 or -1 to 1. And a standard scaler scales it so that you have a standard deviation with normalized standard deviation. And so let's go ahead and just use the standard scaler for this one. Okay, so there's our, with sklearn pre-processing, we're going to import the standard scaler. We'll create the standard scaler, and then we'll use the fit transform. So this becomes our scaled data. Okay, so if I go ds.head, then, doesn't have a head because now it's a numpy array. Okay, so let's just look at the type of ds. Okay, so that's a numpy array. And what we need to do now is put it back into a pandas data frame. And so we'll just go ds equals, okay, and that's going to be a data frame. I'm going to put my numpy array in here and then make my columns equal to my original data columns. And so let's just look at the head of that. Okay, so I've got it back into scaled form now, where I've scaled it with a standard scaler for each of these columns. And often you need this standard scaler, especially not so much for linear regression, but for neural networks or other types of regressors. It works much better if you scale the data with these types of standard scalars. All right, now we want to divide the data. We're going to divide this into the training set. Okay, so we want that to be 80. We're going to make that 80%. And then we'll have the validation, or the test. We're not going to be doing hyperparameter optimization, so we're just going to split it off into the test set here, and that'll be 20% of our data. Okay, so we'll split it so we can evaluate how well it's fitting. and if there's any type of overfitting happening as well. We use the sklearn model selection. We'll import the train test split. So this is a nice one because you can just say, what is my test size? That's going to be 20%. You can say shuffle, so in case all of the MFR data, the low MFR data is at the beginning, it'll just randomly pick from there, and there's our data frame, and then it'll return the two, the train and the test sets. Okay, so there I have it. And maybe I want to just look at the length of both of those. So let's just print the length of train and the length of test. Okay, so it took 1,971 here, and then 493. So again, this is after we've cleansed the data, we've removed any bad data sets, not a numbers, we've filtered it out, the outliers, and then we finally scaled it, and then the train test split. Now the final thing that we want to do is we're not just going to import the data again next time. So we want to actually use a pickle. We're going to take all of these values, the original data, the training data, the test data, the data frame ds, and the scalar s, and then we're going to just write that to a file. Okay, so when I write this, we're going to see something show up in this folder. Okay, MFR data pickle, and you can see the size of it. It's about 0.5 MB, and it has everything that we've worked on up to this point, all encapsulated in that, so we can open it up again in our next notebook, or let's say we're going to close down Python, we're going to come back to it later. It's just an archive of all those values that imports directly back into Python as objects. So that's nice to have. Okay, now we're going to just open up the next one, and this gets into finally the regression. So let's just trace this out. We're going to continue up this route now, and we decide, are there labels? Yes, there are labels here, so we can do supervised learning, and we can do classification if the MFR are discrete values like 1, 2, 3. In this case, they're continuous values, so we're going to use regression for this, try to predict the outcome. All right, first thing we need to do is just import our pickle file back in, and that is going to read it. Okay, so I read it back in, and then now I have data.head. You can see I just have the same data frame like I had for my prior notebook. Okay, let's try linear regression first. This is the easiest type of regression, often a good way just to see, like we were looking at with some of those pair plots, just how well this is going to perform versus the natural log of MFR versus some of our values that we have. Like let's say we just had this X data here, which is just going to be the, okay, so I'm just going to look at this one first, just this relationship. So just do a very simple linear regression, and okay, let's see what I'm going to do here. I just have these two. I can do a polyfit, for example. Okay, so let's see, numpy is not defined. Let me come back up here, and I'm going to import numpy as MP, and come back down here. This is just the polyfit package, but let's just look at some of the for example, the slope and the intercept that it came up with, just with this relationship between the natural log of MFR and the hydrogen ratio. Okay, so there's my slope and the intercept as well. All right, and then what I can do as well is I want to be able to see it on a plot. So let's just go ahead and do X, Z, and we'll make those red circles and then make a label. These are going to be the measured Those are the z values. Okay, and let's do plt show. Okay, plt is not defined as well. I gotta import that package. Okay, so there it is. Okay, so here's my data. Now let me put on the regression as well. And so this is going to be x, and then I'm going to evaluate this polyval, and this is going to be p1 and x. Okay, so I'm going to put in my coefficients, and let's make a blue dot, and we'll say that label is predicted, and we'll have the y value there. Okay, and I can do things like put the legend in there, and maybe if I want grid lines, I can put those in there as well. Okay, so here's our plot that shows the regression versus the natural log of MFR. You can see it isn't doing a very good job. I have these kind of two clusters. I'm not hitting either one of them. I'm just, this low MFR region. Now these are scaled, the natural log of MFR. But it's not really doing that good of a job for this linear regression. So another package that we can use is this stats models package, and it's going to perform the ordinary least squares, or OLS. So let's go ahead and just use this. I'm going to import it. Okay, and I need to just reformat some of the column data. Okay, so just for this case, okay, I'm going to run this regression with stats models, and this one will give us a little bit more than the polyfit, okay, from NumPy. It'll give us an r² value as well. It'll show us on these different coefficients what are the coefficients that it came up with. Okay, so ones that are close to 0. We're going to also look at some of the confidence intervals for those, the 95% confidence interval for those parameter values. So a wider range means that it's less certain. All right, and there's some t statistics, the p statistics, and others here in the table. Okay, you also have things like condition number, kurtosis, and skew, our measure of how normal the distribution is. So some other things you can look at here to see if it's skewed to the right or the left, and whether it's normal or not normal in terms of the distribution, if you have more on the tails or in the middle. Okay, so that's our regression so far. Let's go ahead and go down and visualize these just a little bit more, and also select maybe the best features as well. So maybe we don't want to use all of these for the prediction. We're just going to use a subset, and this is going to be select k best, and we're going to use it for regression. So we're going to import this f regression, and we'll use that as our score function. So instead of classification, it's regression. And so this says, the hydrogen ratio and the pressure are the best predictors of the outcome. And then you can see that bed level is virtually no prediction, which is not very surprising. Bed level affects the production rate. You just have more catalyst and more polymer growing there in the bed. The temperature, okay, again, that might be low just because we don't have a lot of variation. Okay, the catalyst and the monomers are kind of in the next tier. But these are going to be our highest ones right here, the pressure and the hydrogen ratio. All right, so let's go on to machine learning. We have some others as well. We're going to use this this plotting right here, just to be able to look at some of the fits. And this one will show us these surface plots, which are kind of nice. Okay, we're going to now just use linear regression with sklearn. Okay, so instead of with OLS, we'll just use sklearn for most of these. Okay, and so if I run this one, now we can see the r² value. Okay, we're printing that off here. We're going to use a score, the method.score. So in sklearn, we have the fit. Okay, it's going to just use the hydrogen ratio and the pressure, the two that we came up with from here that were the most impactful in terms of select k-best features. And we're going to use those just so we can look at it with a 3D plot. So in this case, we have pretty low r-squared value. And let's see if we can get a little bit better with some of the other methods. Okay, here is k nearest neighbors. We're going to import that from sklearn as well. The number of nearest neighbors, in this case 20. We're going to use this as a regressor instead of a classification. And so it's going to try to look at the data, pick out the 20 nearest ones to the one that we're asking for, and then be able to generate a prediction from that. In this case, we had a slightly better r-squared value at 0.56. Okay, let's go on to support vector regressor. And each of these are described in more detail on the course website. But in this case, we're just going to import them and then call this fit function that's going to do the fitting for us. And you can adjust some of these values right here, some of the hyperparameters, we call them, that help you achieve a better r-squared value or whatever the measure your fit is. Okay, and you can see the surface here. This one's very nonlinear in the surface. I wouldn't necessarily trust this one for predictions right here. Okay, and then we go on to a multi-layer perceptron or neural network. Okay, we can have the hidden layer sizes. I can add additional layers here if I'd like to. And here's the neural network. Maybe a little bit too much there. I'm just going to add the 3, or maybe I can go up to 5. And you can change some of the layers. You can put a lot of layers here, have a very deep neural network. It's going to affect how well it extrapolates if you over parameterize it. So in this case, it says the total number of iteration limits, and we might need to increase those. And so I think it might be something like max iterations. Let's just see if that works. And I'll increase it. It's going to take longer to go, and then we'll hopefully avoid some of that warning message. Especially if you have more parameters in your neural network, you may need more iterations and so you can see this one's not a very good prediction. Here the r-squared on the test set is very poor. So even with more neural network structure, we got a worse performance on our test set. All right, so one of the other things we can do is also some feature engineering. We can look at additional features, not just pressure and the hydrogen ratio. So I'm going to add more of them, and let's just do some of these same regression methods like we did before, or we could just do one, for example, if we wanted to. Okay, but this one I'm going to include more of them now. I'm going to include all of the features, and now instead of this 2D plot where I plot the hydrogen ratio and the pressure versus the fit, this one's going to be a parity plot that shows the measured values versus the predicted values. Okay, so let's just look at that. We have this is our test set, and then this is our prediction. So the y-axis is our prediction, and so if it lies right along this black line, then it's a perfect prediction. So you can see the kind of the measure of the error here. Okay, if we were perfect, we would be here, but we're down here. Or if we were perfect, we were here. So we're very close on this one, but a lot of scatter here. But this is using more of the features. So let's evaluate all of these for k nearest neighbors, for example. Okay, I have a higher r-squared value, but you can see it's grossly over predicting a lot of these high MFR actually under predicting a lot of these high MFR solutions. Let's look at support vector regressors here. Okay, so this one's a little bit better. You know, things are lying kind of almost symmetrically about this black line. Okay, and let's look at the neural network as well. Okay, and this one again, you know, maybe not the best fit. Kind of discrete values that are showing up here. All right, but let's use you know, Keras and TensorFlow instead of scikit-learn. So scikit-learn is good for learning. It's very easy in terms of the syntax. But if you want to scale up and use it on the GPU, I have a very large data set, then you may want to consider using something like Keras or PyTorch or others. So Keras is a wrapper around TensorFlow, and you can, you know, so it simplifies how you create the models. So this is a neural network, a sequential neural network, and I'm going to add dense layers. I'll have a linear layer, a hyperbolic tangent layers here, and then another linear layer. And I can have a different, you know, different loss functions. Like in this case, it's a mean squared error. And I'll choose the optimizer as the atom optimizer. Okay, so if you do not have Keras installed, then this won't work. Okay, but if it's installed, it will run. You can see the different iterations, epochs, as they run. And here we are, we finished. Okay, and then let's go ahead and test the model. There's our mean squared error, and then plot this as well. Okay, so here's our prediction with Keras and TensorFlow. All right, and then here's also intro to TensorFlow and PyTorch. So this is just kind of an additional one that you can run through. I'm just going to run this and show you the output. Okay, let you run it. Here's more of a TensorFlow implementation versus you know, something like Keras as a wrapper around it, where we have our predict, the mean squared error, and then we set this up with a little bit more control over how this optimizes. Okay, and here we are. Here's our prediction. All right, I'm just going to go kind of fast through this. It's more just for showing it. Here's a PyTorch linear regression as well. And okay, so I've imported. There's linear regression. I have my criterion. I'm going to optimize, and let's come up with this plot. Okay, so this is just, it shows the syntax of how to do something similar with TensorFlow and with PyTorch, not using the Keras as a wrapper, but using some of the lower level function calls directly. All right, well, let me just summarize what we've done so far. We've gone through this whole flow chart here with this one example problem. And you'll see that many case studies are very similar to this in terms of, you know, going through this map and deciding at each point, you know, how to construct the data. We didn't do much here with feature engineering. Sometimes we can combine things, take ratios of things, generate different types of features that are going to give us a better performance on the select K best criteria. Also, we might be able to do better if we had more information about the data, you know, what the columns actually represented versus my guesses about them, and apply a little bit of engineering judgment. So at the end of the day, you know, it's using that kind of information to filter out the data, have better data sets. You saw a lot of scatter in the data, and these types of MFR regressions, those would be considered very poor if you just had those results. You know, you'd want something to be much tighter than that. You want to stay within maybe 10% of the MFR result, or even closer for the property prediction. So you want to be able to predict reactor conditions that lead to a very tight distribution there. But you'd follow the same strategy to develop the regression. You might also include some of this physics-based digital twin to be able to supplement some of the data or to validate some of the values that are coming out of the predictions. Well, I hope you enjoyed this, and there are many more case studies that we're going to be going through. You can see some of the applications here, and we'll be adding more as we go. And then if you missed some of what we covered, there's quite a bit of data engineering here that I recommend going through. If you're just starting out, come to the introduction to this. There's on the schedule, it shows how to get started, and you want to start with some of these data science modules that just step you through some of the basics of regression and classification.